Okay, so in this video we're going to be looking at the elimination reaction. We're going to look at the practical setup. We're also going to look at the last of the reactions, and that is with halogenoalkanes and cyanides to make a nitrile. Okay, so we're on page 16 of your notes and we're looking at the reaction with concentrated alkali in ethanol. So again, the solvent is very important here. If we did this reaction in water, we would get the alcohol. Because we're doing the reaction in ethanol, we're going to get the alkene. So we've got some quite dangerous chemicals we're handling. Halogenoalkanes tend to be harmful, so halogenoalkanes. Flammable, well, we're using ethanol, and also the halogenoalkane is also flammable, and corrosive, well, we're using hydroxide. Hydroxide, and quite concentrated hydroxide, is very corrosive. Corrosive means it burns on contact. So this is my apparatus setup. In here, this is where I have my mixture. So I've got my potassium hydroxide dissolved in ethanol, and I've got my halogenoalkane. It's held in place by just some ceramic fibres. Okay, that's just to hold it there and to stop, because these are all liquids, to stop them sort of sloshing around the place. We gently heat it. Okay, the gas comes off, we hope, and we collect it over water, so we get the gas bubbling up here. Okay, and we're going to collect about 2 or 3 test tubes of gas. Okay, so one of the things we need to be very careful of with this is preventing what we call suck back. If we stopped heating our test tube then too quickly, then it could draw water back from the water trough, and the cold water hitting the hot glassware is not a good mix. So the way we prevent suck back is that we remove our delivery tube before we've stopped heating. So we keep heating it, we remove the delivery tube, and then we can check whether it's got any water in the delivery tube. If it has, we just heat it for a little bit longer to push that water out, and then we can stop heating. So we're going to do 3 tests on our sample. We're going to test for flammability, we're going to test with bromine water, and we're going to test with manganate in sulfuric acid. So what you should see with the test for flammability is a yellow flame, because we're burning a hydrocarbon. The bromine water should decolorize, and so should the purple manganate. Remember, this is bright purple, and it should also decolorize. Sometimes you'll see it go a little bit brown. If it does go brown, it's usually because you've not got enough acid present. Okay. So, what is the functional group of the new gaseous compound? Well, we've made an alkene. Okay, and this is one of the few ones with halogenoalkanes which is not nucleophilic substitution. This is an elimination reaction. So in this case, the OH negative is acting as a base. Okay, so an oily film may appear on the water surface. Basically, that is unreacted halogenoalkane. So the halogenoalkane has vaporized, gone through the delivery tube, and because it's a liquid at room temperature and pressure, and it doesn't dissolve in water, it appears as a oily film. Okay, the reaction using our displayed formula, well, we're going to start with our halogenoalkane, which is our bromo halogenoalkane, and we're going to do our elimination reaction. So we're going to remove a hydrogen from an adjacent carbon. So it doesn't matter which one I take. I can take this one, I can take it this way, it doesn't really matter. But I'm going to end up with that double bond there. Okay, and I've still got my 2 H's and I've got my CH3 and my CH3. So I've made methyl propene. Okay, nice and straightforwards. Okay, so the next question is looking at whether or not we would produce HBr gas. Well, the HBr gas would form, but because we've got hydroxide knocking around the place and this is an acidic gas, it's likely that the HBr that we produce would react almost immediately with it to produce potassium, bromide and water, because we get the reaction between the hydrogen bromide and any spare potassium hydroxide. So those two react together to make potassium bromide and water. This you can think of, it's an acid, very like hydrochloric acid. This is hydrobromic acid. It's actually a slightly stronger acid than hydrochloric acid, so it's going to react very quickly with the potassium hydroxide. The reaction then, or the reactions, I'm just going to do the products with bromine and with acidified potassium manganate. I'm going to assume the bromine is an organic solvent, and again we would get the same carbon skeleton as before, but this time we've got the two bromos on there, like that. That's your simple electrophilic addition mechanism, and then we would also get the reaction with acidified manganate, and that makes a diol. Okay, so that's so simple. That's we classify as either an oxidation reaction, or you can also classify it as an addition reaction. Okay, so the last reaction in this pack is the nucleophilic, and sorry, that should be nucleophilic substitution. That's my mistake. Reaction. And this is a reaction with potassium cyanide. So it's potassium cyanide and halogenoalkane, and those are my reagents. Do not get it confused with the reaction with the carbonyls, which is potassium cyanide and hydrogen cyanide. There's no hydrogen cyanide involved in this case. We're simply doing a substitution reaction. We just need to use potassium cyanide on its own. One of the classic mistakes people write is hydrogen cyanide and potassium cyanide, and it won't work, or won't work very well, with the halogenoalkane. So we again have alcoholic KCN. In other words, we've got a potassium cyanide dissolved in ethanol. Ethanol, remember, is a very good co-solvent because it has both polar and non-polar characteristics. It will be able to take both the halogenoalkane and the cyanide into solution and allow them to mix. Okay, so again, you've got your general reaction here. You've got your halogenoalkane reacting with your potassium cyanide. It makes a nitrile group, C triple bond N, and your potassium, potassium chloride, bromide or iodide. So if we take this as an example, here we have this molecule. We're basically going to just replace that Br with a C triple bond N, and we get potassium bromide as our product. The thing to notice in this case is we've gone from an eth, we've gone from bromoethane to propane nitrile. So we've increased the carbon chain by 1, and this is a very important reaction. This, along with Grignard's reagents, is the only time you can actually get, or the only way you know to get, an extra carbon onto a chain, or increase the carbon chain length. So if you ever see that in a reaction, you'll know you're going to have to use either a Grignard's, or you're going to have to use a cyanide ion somewhere. Okay, so we're going to look at the reaction between 1-chlorobutane and potassium cyanide in ethanol. I'm going to name the product. We're going to look at this reaction, and I'm actually going to do the mechanism for it because it's quite simple. It's very similar to the mechanism with the OH negative, because it's a very simple nucleophile. So we're going to start with our 1-chlorobutane. So we've got 4 carbons. Okay, in a nice simple molecule. And we've got our polar bond here, so delta negative, delta positive. We've got our cyanide ion, Cn, negative. That's going to attack that delta positive carbon, pushing the electrons out there. I'm not going to draw the transition step, okay, but I am going to draw that bit in. So then we just get a very simple product. We've got 1, 2, 3, 4. We've now got 5 carbons on our chain. It's a very easy way of extending the carbon chain. And we obviously have kicked out the bromide. So we get potassium bromide as our product. If we started with potassium cyanide, we get potassium bromide. And our product, we've now increased the number of carbons in our chain. So we've gone from 1, 2, 3, 4 to 1, 2, 3, 4, 5. So that's pentane nitrile. Okay, so you've now got 5 carbons in your chain rather than 4. Okay, so the last reaction we're going to look at in this pack is 2-iodopropane, again with potassium cyanide in ethanol. So we're going to start with our prop molecule. We have an iodine on the second carbon, which is why it's 2-iodo. And again, I'm going to draw in my cyanide ion. This again is my polar bond, delta negative, delta positive. So this is going to attack the carbon. That's going to push the electrons onto that iodine. And we're going to get as our product, we're going to keep the 2 CH3 groups on the ends, but we're going to have added in that cyanide. And we're going to keep that H. Now this becomes my longest chain because it's the one with the functional group on it, and this becomes my side chain. So this will be methyl, and this is propane nitrile. So meth because it's got 1 carbon here. This is my longest chain, which is 3 carbons, so it's propane, and it's propane nitrile because it's got a nitrile group on the end of it. Okay, so that finishes off the reactions in the pack, and that actually finishes off most of the work in the pack. The only thing left to do is the spider diagram, and I'm going to do that in a little bit more detail because I remind you that your benchmark 4, which is coming up after the half-term break, will have all the organics on it. So I'm going to do a little bit bigger spider diagram than I would normally do at this stage. But that's all for now. So take care, stay safe, speak to you soon. Bye-bye.